Hello, welcome back. So in the last video, we saw how we can kind of impose a virtual spring through control. So having a controller that makes our system behave like a mass spring system. And with that, we could transform this unstable system to a stable one. And if you remember, this is the root locus of the system. As my virtual stiffness, K, or the control gain, increases, the poles of the system, one of them being unstable, get closer and closer to the origin. And after that, they will start to separate from each other on the imaginary axis. So if my K is large enough, I'll have two complex conjugate poles or eigenvalues that make the system behave like this non-diminishing or everlasting oscillation. So that was the first attempt that we had on controlling this system. Now let's have a second attempt, a better one. Let's try to impose a dynamics onto our system such that my angle kind of oscillates back and forth and in the end stops at an upward position. So this is the desired behavior of my system. And I want to realize that behavior through feedback control. So if you remember, this damped oscillation systems meant that I have my eigenvalues of the system has to be it has to have a negative real part plus some j omega. So in the previous example, this sigma was 0, and my poles or eigenvalues were on the imaginary axis, and I only had oscillation without any decrease or increase in magnitude. So if I want my system to behave like that, essentially what I want to do is to bring the poles out of the imaginary axis and into the left-hand plane. So these two poles, well, not including that, these two poles will have the response that I desire. So they will generate that kind of response. So it would be ideal if I can create a feedback controller that kind of shifts the poles of my system further to the left, to the more stable side. The further out I am, or maybe I can try to plot it here. So this exponential e to the minus sigma t, or I have a, let's call it sigma, and sigma is negative. So let's call it like that, e to the sigma t. And as I make my sigma more and more negative, shifting my poles further out, I'll have a response that diminishes faster. So I'll have something that looks like this, quote unquote, more stable system. So let's try to realize a controller that does this, and this method that I have, that I specifically choose where the poles of my system is, very aptly named pole placement, pole placement method, that I think, okay, I want my poles to be here, and then we go and design a controller such that the feedback loop system has that poles. So let's try to do that. you think this is enough space? I don't think so. All right. So to do that, without getting into detail why this may or may not work, let's take my torque that is applied here to be kind of a feedback that measures my state, theta and theta dot. Those are the two states of my system. And through a kind of matrix gain with gain elements A and B, I can calculate torque. This is called a full state feedback. So the output, the control output, torque, is a matrix manipulation by the entire state vector. So my goal is to design these A and B's. And remember, if a system that has this property, the characteristic equation that we had, if you remember, was lambda squared was it plus 2z omega n lambda plus omega n squared. So this is the characteristic equation that gives me this kind of behavior. It is depending on the value of this damping ratio z, I can have an underdamped system the way I like. So this is a mass spring damper system with damping coefficient determined by z. Okay, let's plug in this controller into my system. So now my system looks something like this. So I have my pendulum. This is my system. And the two states are theta and theta dot. I take this and feed it through a control gain K. I'm going to write it like this to demonstrate that this is a matrix. And this gives me my torque. And I feed my torque to the system. Hopefully this feedback loop gives me that. So going back to my state space equation, I have d over dt of theta dot equals 0, 1, g over L 0 times theta dot plus I have now this torque, which I'm going to replace with AB theta dot. This is my new system equation. And I can factor out, wait a second. That's not good. What do I want to write? That, right, this is not, so I missed the B matrix. So my B matrix was 0, 1 over L times torque. Now my torque is A and B, theta dot. Okay, that's better. Now let's do this. So let me rewrite this 0, 1 G over L 0 theta dot plus. Now this I have 0 times A 0 times B 0, 1 over L times A, so I have A over L, and 1 over L times B B over L times theta theta dot. And this one is, I can factor out these state vector. So I have 0 and 0 here. G plus A over L and B over L times theta theta dot. And this is my now closed loop A matrix. And what I want to do is to find eigenvalues of the system. So to do that, maybe here. So to calculate eigenvalues of A, I solve for determinant of A minus lambda I. So I'm looking for determinant of A minus lambda I. So I have minus lambda 0 G plus A over L and B over L minus lambda equals 0. And now this is lambda squared minus B over L lambda. Wait a minute. This was 1. 1 minus G plus A over L equals 0. So this is the characteristic equation of my closed loop system, which I want to be like this. So this is the desired characteristic equation. What I need to do is choose my A and B values such that this equation is the same as that equation. So let me write it down here. C plus 2z omega n lambda plus omega n squared equals 0. So comparing these two characteristic equations, that's loud. The fan started. It's very loud. So these two coefficients of lambda should be equal. So I have minus B over L should be equal to z omega n. And the constant, these two must be equal. What happened? Minus G plus A over L plus omega n squared equals 0. So I have these two equations, and from here I can calculate my B is minus 2L z omega n, and from this one I get A to B. I do mental math, which I'm not good at. L omega n squared plus G, I hope. Does that make sense? Has to be negative for some reason. All right, yeah, it is. I did it. Let me write it down. So G plus A over L equals omega n. So L omega n minus G still doesn't work. Maybe it is correct. Maybe my note is not correct. Omega n. Well, I don't know. Something is fishy, but let's go with this. Let's go with minus g. If it turns out incorrect, minus g. I still don't like it. Probably it is what it is. Okay, anyways, it is what it is. So these are my two control gains, A and B, for the full state feedback gain K. So if I know my damping ratio, my desired damping ratio sigma n, and my desired natural frequency omega n, I can design B and A and make this control law or feedback control calculation based on the current states of the system, make this feedback loop, and doing all of that, my system will behave the way I desired. So this is an example of what we can do with pole placement. We can think what our desired behavior of the system looks like, figure out where the poles are, design a controller that shifts the pole of the closed loop system to those locations, and in the end what I get is the system that behaves the way I want it. So let me go back to here, that maybe originally I mentioned in the previous lecture that the goal of control is to get a system and overwrite the dynamics of it, and this is exactly what we did. The original dynamics was determined by these two poles, one of them being unstable, and through feedback control I changed the system to one that behaves completely differently, and the dynamics is now described by these two fully stable and far from the imaginary axis poles. So maybe one last little remark before I run out of space is, so my torque is this matrix times my state vector. I can do that and write it as A theta plus B theta dot I'm still thinking about this. Why is it like that? Anyways, so what you see is this B is a damping system, and this A is kind of a virtual stiffness, or have virtual stiffness and damping imposed by this controller. And one other thing that you can consider, this B is multiplied by the derivative of theta, and A multiplied by theta itself. So if we take the theta, the angle of the pendulum, as the output of the system, so my theta y is the output is theta. What I have done is create a controller that is proportional to output and proportional to the derivative of the output. So the proportional component A is called a proportional control or control gain, and B is the derivative control gain, and P and D, what we have constructed, is probably the most widely used controller in industry, called PD control, that acts on the value of your signal and its derivative and calculates the control output. So this PD is extremely powerful, and it can stabilize extremely unstable system, including handling some level of nonlinearity, and it is so easy to implement using just basic electronics. And electronics and hydraulics and pneumatic, all of these systems have their own implementation of PD controller using either resistors and capacitors and things like that, or valves and what else? Valves and something else in hydraulic and pneumatic systems. So this is a very easy controller to construct or to implement, and it is very powerful in the things it can do. Let me do one little thing before I erase. So here, instead of writing A theta plus B theta dot, so a different controller, I could write A theta minus A theta desired plus B theta dot. So essentially what I have done here is change the resting length of my virtual spring to a different location. And in doing so, my system now goes oscillate about that desired position and stops there. And what this controller does is, I'm running really out of space, is called a servo control. Servo control. A servo control that is realized through a PD controller. So I can, I don't know, in a computer or with any other mean, define a set point, like I want my system to go to 82 degrees, and this controller moves the system to that desired position. So okay, so that's good. I kind of fitted everything in here. I just have a tiny bit left about PID control. Let me clean up the board and I come back and wrap up. So this is the last board of this lecture, this course actually. So I'm a little emotional. So we're talking about control, and it is not possible to talk about control and not mention the king of control, which is PID. PID, we just saw PD, the kind of a special case of a PID controller where the integral part is, it doesn't exist, it's just maybe zero. So going back to perhaps the idea of transfer function, just to maybe refresh your memories as well. So I have the system, let's call it U. I have the system, it receives the input U and output, and gives you output Y. You can create a feedback and compare the output of a system with a reference signal. For instance, in the pendulum example, the output was the actual angle of the pendulum, and this reference would be the desired position that I want my system to go to that position. So I can compare those and kind of the difference, take the error between the actual and the desired values, and then feed that to 3 separate control modules, if you will, the integral module, the proportional module, and the derivative module, and calculate the output of each and then sum them together. That would be my total control control input that I can feed to the system. So this whole thing is my control gain H. Let's go a little bit into what each portion does. So first one is the proportional. It is, so if I have this signal error, the output is acts on error E, and by that we mean it's proportional. The output of this module is proportional to E, or it is some Kp times error. What it does, we just saw, it feels similar to a spring, so kind of acts like a spring. Kind of gives you this compliant behavior in the system. And what other thing it does? So just through a feedback that only involves this proportional aspect, what it does, it tries to drives E to 0. So it tries to suppress the difference between actual and actual output and the reference values. The next one, the derivative, we also saw it. The derivative one, this one acts on derivative of E, or it acts on E dot, and what we get is some Kd times E dot. So it calculates the error, the time derivative of that error, and then multiply that by some constant value Kd, and that is the output of this module. Or in Laplace domain, you could write it as Kd times SE. So usually when we are kind of writing these in block diagram, we do KDS. So this is the block diagram version of this. E comes in, output goes out. So what it does, in the pendulum example, it acted like a damper. So it kind of tries to get rid of the excess oscillations. That's one kind of effect of this. The other effect, or maybe I should have mentioned this, that by increasing, let's go back to here. By increasing Kp, you essentially makes your system more sensitive to errors, and that two things happen. One is your output will become closer to the reference value, That's one thing. The other thing is it makes your system move faster. So the response, the control input will be stronger given the same amount of error. So by increasing your gain, you are essentially making your controller stronger, and it increases the speed of your output trying to reach the reference value. The derivative one also, well, I just mentioned, it gets rid of the oscillations by acting like a damper. So it eats into this oscillatory behavior. Also, because it acts on the speed of error or the derivative of error. So if your system, your reference jumps quickly, that leads to a very large derivative, and that also causes the system to kind of increases the speed of your system in general. And the last one, the integral. The integral controller acts on integral of E, or it is some Ki times integral of E dt. So integral from maybe time 0 to current time, we accumulate all the errors that have been in the system so far, and then multiply that by a constant value. That would be the output. And kind of in a block diagram way, this is Ki, and remember the integral is 1 over s. So this is the kind of the block diagram version of the same thing. What it does to the behavior of the system is a little more difficult than these two on their own, because when we have an integral, this is an ugly integral, it actually increases the order of a system. So for instance, in our pendulum problem, it was a second order system because it was 1 degree of freedom. It had inertia, second order. But if I include a derivative, it increases the order of a system to three orders. So essentially, after that, you don't really have a mass and a spring and damper system. You have a system that is slightly different. So in some sense, it acts a little, no, you cannot just call it, I don't know, it acts like a damper or it acts like a spring. It is tempting to say it acts like inertia, and it kind of does that. So what you get, two effects happen when you include an integral controller. One is because it is acting on the cumulative error, if your proportional controller cannot get you to the desired point or desired reference you want to be, this controller keeps building on the existing error and increases your input until you reach your desired value. And it is very easy to show in my pendulum example that if my reference is such an angle, because there is gravity, there's a spring on its own. If you just have a spring, doesn't matter how stiff it is, there is still some deflection left in the spring. So you will always have this, what is called steady state error, this steady state error, if you only have a proportional controller, aka a virtual spring. So this spring cannot get rid of this steady state error. To get rid of that and completely come to the position that is your desired position, you need to have an integral controller that over time, when your spring kind of gave up, it starts to accumulate error and increases the torque onto the system until your pendulum comes to the angle that you desire. So it gets rid of steady state error, steady state error. And another effect that it has kind of resembles an inertia. It increases the oscillation and overshoot of the system. Increases overshoot and oscillation. And kind of to see this effect, imagine you have a system. So you have given it a reference. So at the beginning, there is no error. And all of a sudden, your reference jumps. So you start accumulating these errors, and your system starts to move forward. When you get there, you still have all these accumulated error beforehand. So your control is still pushing the system forward. So it overshoots. Now you're accumulating negative error until it's 0. And then the system comes back. You have these negative errors, and the system goes back and forth because you are integrating the error. And the same effect is kind of involved when it increases the overshoot. So, okay, that is kind of an intuition about what these controllers do to the system. And the last bit I have, just because we like equations, let's find the closed loop transfer function of this whole system from the reference to output. So I'm trying to find G of closed loop, which is Y over R. So if I take this whole thing as the controller transfer function, call it H, what I have is this system that I have H goes to G, comes out, feedback, plus, minus, this is R, this is Y. So a shortcut to remember how these feedback systems, their closed loop feedback transfer function looks like. It is open loop transfer function over 1 plus closed loop transfer function. And by that open loop, I mean open this doesn't exist. So open loop is G times H, so it is GH over, now I close it, now I have this closed loop, 1 plus this whole thing, whatever exists in this loop, 1 plus GH. And my H is HI times E, so the output is HI times E plus HP times E plus HD times E, or HI plus HP plus HD times E, or the whole transfer function is HI plus HP plus HD, which is integral is Ki over S, HP is just Kp, plus derivative is SKD, And this one is Ki plus Skp plus S squared Kd over S. Now I plug that here, so my G closed loop is going to be G times that, Ki plus Skp plus S squared Kd over S divided by 1 plus the whole thing. I do it G over S, Ki plus Skp plus S squared Kd, which with some manipulation, so I can, what can I do? Okay, so I checked my calculation. It had to be positive, negative, because it's unstable. It's an upward pendulum. And if you do all of that, plug in everything, you will end up with this differential transfer function that is now third order instead of your original second order system. And this showed up because we had this division by S in the integral. It showed up here, it showed up there, which multiplied by the existing S squared, the dynamics of the system, gave us a third order system. Okay, and given the right parameters, Ki, Kp, and Kd, you can move around and shift the position of the poles such that you get the desired behavior. For instance, the speed by which the system rises to the reference value and suppress the amount of overshoot and all of those. Okay, so that's it for the course. So this really wraps up the entire course. Let's take a moment to think what we did. We looked at, originally we started with just modeling a system, writing the differential equations that govern the dynamics of the system. We tried to solve those differential equations using Laplace transform to see how the behavior of a system just looks over time. That was one thing. Then we moved on to transfer functions as a kind of notation or language that we describe the system. For instance, a use case of it was shown here. We could do a lot with those transfer functions, including an easy way to do frequency analysis, an easy way to look at the stability of the system. And what else did we do? And looked at a few, I think, time domain analysis of the system. So that was one notation or toolbox we used. The second one, we moved on to state space, which was a little, in my opinion, stronger and more powerful notation. And we used the same method using eigenvalues, which was the poles of the system, to look at the stability. We visualized the system using phase portrait, which was, in my opinion, again, very powerful way to think about the system. We looked at frequencies, and mostly natural frequencies of multi-degree of freedom systems. And what else? Stability. Did I mention the stability? And we also looked at the stability, which coincidentally, the poles of the transfer function and the eigenvalues of a state space system are the same. And we could study stability of the system using that. And finally, we very briefly in the last two lectures touched on control and how we can use the topics that we have learned and topics that we haven't learned, and there's a ton out there, to design controllers and make our system behave in a certain way. So, okay, that's all I have for you, literally, and hope it was something that you benefited from a little, at least, to be familiar with what dynamical systems are and how we can analyze them. By no means we have covered everything, but I hope it was a good introduction to the topic of dynamical systems. So with that, I leave you with this board a little bit to think about, and see you later.